This may be a good time to show you the documentation. So it's at docs.obspy.org. Might be useful to just open this in a tab because you will definitely need it later on. And it has, just very quickly, it has a short tutorial here. That's usually reasonably up to date, I guess. It introduces you how to do all these things in ObsPy. How do I go back? Here. It has a gallery. So that's just plots of all the things you can do with ObsPy. So there are a large number of plots that directly come out of ObsPy. If you want to know how to do one of these, you click on it, and it shows you the code that was used to generate that particular plot. But the actual meat is in the library reference. So those are all the separate modules ObsPy is made of, and you can work with these. So usually most things are very well documented, and you can read how to work with them. So I just used the select method. So I can just, up here you can search, you can type select, and it shows you, now we use the stream select. If you want to know what it's doing, you find the select method of the stream object, and then it shows you here what arguments it has, what it does, the sort of documentation. Most usually also have examples. So if you want to know how to use the select method, you look it up and you see some examples, and it should be pretty clear what's happening. Okay, it's really important, any kind of Python, most programming, is learn how to read the documentation, learn where to find the actual information you need. Okay, so here again, I only select the vertical components. This should give me then 2 traces. Another thing I said before, a stream is a collection of traces. In many cases, you might only want 1 trace of that stream or a certain slice of it. You use square brackets for that. Just like again, Python is 0-based. This will give you the very first trace. You can, the same, like almost all the methods also work on trace objects. What happens in practice, if you call like stream.filter, it will just loop over the traces and apply the filter to each trace. And there's some basic processing. Again, please note these modify the existing object. So you can write them on one on the other, and they will keep adding steps to the processing chain. The common thing is like to remove a trend from a data. So this will just remove a linear trend. It will fit the best fitting line. We also have like just pick the first and last sample, pick the mean, or we also have some higher order detrending function for like tides or whatnot. You had a question?
Yeah, so when you say modify the existing object, is it like just modifying the data in the memory, or is it like saving the data somewhere?
No, it's actually modifying the data in memory. Sometimes we internally create a copy, but after the function has run, the actual data will be modified. Which for some algorithms is also more efficient. Yeah, because if we did not modify it in place, you would have to assign the copies all the time. It would make for a very awkward workflow. And in most cases, that's what you want to do. Just keep that in mind if you don't want to do it. Okay, next thing is like you want to taper. So tapering means to put the ends towards 0 for like further operations, which if you go to the frequency domain, you have to do. The various number of tapers, you can say the type. We have like 20 different windows, I don't know. That's a Henning window. And the max percentage tells you the max length at each side. So it's a 5% window at each side for this. Then you can filter. Again, there are various filters. The default is like a low pass. That's a Butterworth filter. That's the corner frequency. And again, there are many more arguments to it. But you will see all of this later. And then you can plot it. Okay, that's how you work. That's the basic workflow of how to deal with waveform data. You read it, and then you apply the methods. And at the end, you hopefully have what you need. Okay, and what you can also do, once you have something, all of these stream and trace, they all have a write method. It's because you don't only have to get data in, you also have to get data out. And you do it with the write method. You call the stream, you call write, you give it a file name, and then you say the format you want to save it to. This will take whatever it has and dump it to a miniseed file. So it also makes ObsPy a pretty good tool for data conversion. You read it and write it to something else, and then maybe use your other tool for the rest. Okay, any questions so far?
So on that, if you were, say, to specify SAC,
yes.
Write
yeah. If you do this, in this case we actually write 6 files.
Oh, right, okay.
Because it's 6 traces. So SAC only can store 1 ID per file. Yeah, but most file formats can actually write multiple ones. And this will just create 1 miniseed file. Right. Yeah, SAC is special in that sense. But we actually go to SAC right now. So the SAC file is the custom format of the SAC code. It has a very simple header, and it stores binary single precision floating point data. That makes for a very simple and efficient file format. A big downside, it's only a single component profile, and there's no concepts of gaps and overlaps. So if we need to deal with multiple components or gaps in the data, it's kind of awkward to do with SAC. It's used a lot due to SAC being very popular, and also because there's some basic additional information in the header, which is actually quite useful for many practitioners as knowledges. That's why it's used a lot. You call the read method. You notice you don't have to tell the file format. We detect the file format and then call internally the correct routine to read the data. You can then again print it. Now you see here, I print the meta information of the SAC file. So if you read a SAC file, the stats dictionary will have a SAC attribute with the information from the SAC header. And that's a bit different from the mini-seed header you see here. You have all these SAC headers you would expect. Okay, and by default, it only shows you those that are set. If they're not set, like it's -1, 2, 3, 4, this magic number, it doesn't show them. And you can just set them. If you write it again, they will end up in the final file. So you can quite naturally work with SAC files as well. You can again plot it. That's quite a random file here. The plot looks funny. And once again, as I said before, you can just write it. You use the stream object, call the write method, and the file name, and then the format you want to write to. Yes?
What are the headers that are required in order for a trace to be read?
The headers? The SAC headers, you mean?
Yeah, for example, what are the headers that are essential?
For any kind, well, in theory, it's the sampling rate and the start time, the time of the first sample. That's probably all you really need. I mean, network, station, location are nice to have, but that's not what you need. But to make sense of a time series, you need the first time, you need to be able to locate them in time, essentially. And hopefully have some identifier to locate them in space, which the seed identifiers do. But all file formats provide that information one way or another, so. But with the SAC, if you want to read a SAC file, of course, it has to be a valid SAC file. There's no room for error there.
Do you notice any changes in efficiency whether you specify the file type or not? For example, you can read a SAC file and file type equals SAC.
Well, if you can do this here, it's a bit faster. If you know the format, you just skip the format detection routine. And that also makes it, if a file is not fully valid, ObsPy might still be able to read that, but the detection routine might not. But we hopefully start to read out these things. You can specify the format, but just skip the detection. It's a bit faster.
In the third line there is no print statement.
Oh, okay. What happens, you see here, this is actually like, okay, if you print something, it goes to standard out. That means it goes here. That's the print statement here. In the notebooks, the very last line, it just shows you in the out statement, it shows you the representation string of that object. So whatever you put last, it will try to print that to screen. That's just what the notebook does. It doesn't have any meaning. You can also print this and it looks a bit different. You see now it's done by this, but the notebook has some kind of nice way to print dictionaries, so it prints them alphabetically as well as one by one. It's easier to see. Okay, that's for this waveform data. The overview next one is the station information. Now you've seen this cartoon in the talk before. So the station data contains information about organizations that collect the data, the geographical, sometimes the geological information, as well as the instrument response. In practice, what you really need it for is the station location and the instrument response. That's probably what most people need. It comes usually in one of three formats, or maybe four. One is a dataless seed, so the full seed format. It's very complete, but pretty complex and binary, but it's still used a lot. For example, you can still get it from data centers. The ArcLink protocol uses it. The next one is the RESP file, which is a strict subset of seed. So it's an ASCII version that contains only the response information from full seed files. So this particular one does not contain station information or like location like coordinates. And the next one, which if you can, please always use that. Use station XML. It's essentially the successor of the seed format, but it's an XML representation of mostly the same information. And it's based on XML. It's the most modern format, and it's what the data centers nowadays tend to serve. If you have a choice, please use station XML, the best way forward. And ObsPy can work with all of them in some fashion, but we will here today we'll only focus on station XML. Okay, and you can see here they are XML files. So if you go to the data, the old station, you print the first couple of lines. That's an XML file, which It is in a certain sense human readable, but they tend to be extremely long. So nobody looks at them directly. You do some other way. You use ObsPy to read it, for example. So you can just here, again, to read the station XML files, you import ObsPy. And this time, you use the read inventory method and not the read method. Okay, people sometimes ask, why can't you use the read method? We could do that, but then the same method function might return different objects which we don't want. This object, no matter what you do, it always returns an inventory object. It's just a much nicer way of structuring your code. So once again, just pass the file name. And you note you don't have to specify the format. You of course can, but it figures out the format and parses it to an inventory object, which you can then print. That here is an example. That's actually, I think that's an Italian station XML file. You see a couple things. You see when the inventory was created. So that's usually when you request it from the web service, for example. They put the timestamp there. You can see who you sent it. So this particular file was created by a SysCom3 installation at the INCV in Italy, and also what it contains. And it contains the full hierarchy. So you see the networks, has 3 networks, 9 stations across these networks, and 47 channels. These station XML files can be pretty large, which also sometimes quite convenient because you only need one for all the things you do. You can plot them, so you can call inventory.plot. By default, it shows you a global map. If you know you have a bit more regional network, you might try a different projection. So local is our custom projection, which tries to zoom in region and tries to make a reasonably nice map representation. If you execute that, you see here, okay, those are all the stations. That's in northern Italy, and that's where the station is located. The same as the waveform, you can also select subsets of information. So now you have this huge inventory object, but you only care about some information. You can call the select method. You can select the network, station, and channel. You see here most of these also support wildcards. So here's a question mark. This will just match anything. So it will select the BHE, the BHN, the BSC channels. That also works for all the other things. Just a simple and quick way to query inventory objects. And then now instead of calling a plot, I'm going to call plot response, and it will show me a boat plot of the instrument response for those channels. And that's just the minimum frequency we'll plot it for. If you execute that, you see here it will show this thing. So that's the amplitude response and the phase response. You see here there are 3 lines, but you only see one. That's because they're all exactly the same for this particular station, which is mostly the case. Mostly 3 components have the same response. Sometimes not. Okay, I guess you can all read these plots. I assume so.
What's that one mean at the very top?
Oh, that's the frequency at which this is the sensitivity of the instrument. That's the frequency at which this is defined. So you can read this at this point. You have this sensitivity. It's always usually just defined at one point. Okay, that's a pretty good instrument. Very flat passband and whatnot. That's very good if you have an instrument, an unknown instrument, you kind of want to look at it. How does it behave for my data? You might want to check that out. And the other common thing, what you need are the coordinates for a station. Now you don't need to manually go into this inventory option, find that information. There's a get coordinates method, and you just pass the full identifier, and it gives you back a dictionary with the 4 coordinate tuples. And this multi usually have latitude and longitude. In VGA is 84 coordinates. And you have the elevation of the ground level compared to the ellipsoid, but you also have a thing called local depth, where this is the burial of the sensor beneath the local surface. And I think they want to introduce a 5th one, which is like something within water seismometers. But this will just go there. And once again, you can write these, okay? You can modify these if you want. Like say, okay, I only need the vertical BHH channels. I select a subset and then call the write method. Again, the file name, and they tell the format to write to. Okay, station information is a bit different because you can write to different formats, but only station XML is really complete. So you will lose information when you write it out. Something to keep in mind, that not all formats are complete. You might lose information if you convert data, but that's just how it is. You can change that. All right. The third of the bunch is event data. So, as I said before, events are stored in catalogs. Catalog is just a list of events, and events contain all kinds of things. This is actually very complex, but that's a consequence of how it is in real life and how Quake ML is organized. And event data is usually if you get it from a data center, it's usually in QuakeML. In practice, it's oftentimes it's the NDK format from the global CMT catalog. Or many of you are familiar with waveform solvers, and they use a format called CMT solution file. CMT solution format, that just shows you one, that shows you the time, the location, and the full moment tensor. Here's it in dyne per centimeter. Be a bit careful, but that's one of the ways events are specified in cosmology. And data centers, on the other hand, they usually offer QuakeML, which is a more complete format, but it is surprisingly complex in structure. But on the other hand, it can store complex relations. So it can store the origin to which a magnitude belongs and so on. It's really a complex hierarchical relations between all these various pieces of it. And in ObsPy, we essentially directly reflect the QuakeML structure. But in many cases, you don't really have to worry that much about it. So once again, to read any kind of event file, this time instead of read inventory, we call it the read events method, which just takes the file and parses it to a catalog object. We'll detect the file format and give you a catalog object. You can once again print that. You see, okay, that's just only contains a single event, and it contains some basic information, the origin time, latitude, longitude, and the magnitude, as well as the type of magnitude. As I said before, catalogs are a list of events. So to get the very first event, you type catalog.0, that's it. Okay? Once again, exactly the same as with the stations, you can plot it. This time we're going to choose an orthographic projection to see where the event is, and you see it's an event somewhere in Chile. But please treat these plotting methods, they are intended to give you a quick view into the data. If you want to produce a plot for a paper, you will most likely have to modify it so strongly that it's easier to make your own plot. These are just like quick previews. What do I have? Show me. Once again, same thing as with all the other data formats. You can write them again and choose the format. So if you want, okay, this is a QuakeML file. No, sorry, save it to this file name and store it as a QuakeML file. You can choose a number of different formats here. And once again, that's usually a lossy conversion. So you will lose information in the process of doing that. Okay, and now we're almost done with the quick introduction of everything. We'll get to something more hands-off, more hands-on. Let's show me one more thing. So here we have a file. It's a single file that contains all the events from 2014 in the global CMT catalog. In this case, it's actually an NDK file. You can read it, you can print it. It takes 1 or 2 seconds because it's a big file. And you see now it contains almost 2,500 events. So that's actually a fairly convenient way to work with the largest number of events. You can again plot it. It hopefully shows the blade boundaries and whatnot. You see here now you have a plot. Very quick and easy way to get a plot of all the events in the global CMT catalog. Just to judge you what's up. You see it says the events, the size depends on the magnitude, and the colors respond to the depth. So you see most are fairly shallow, with a couple of deep ones here.
So in that case, those files have more information than in the CMT solution. Do you save that, or is it mainly just saving the same information that would be in the CMT solution files?
NDK is exactly the same as CMT solution almost. That's just the.
There's more stuff in there.
Let me. Oh yeah, you mean the other? Yeah, we store that.
There's
The hypercentral and.
what kinds of mantle ways were
Yeah, this we store. It's in the format. Like what we actually store is a representation of how QuakeML works, which is the most complete format. So yeah, we store everything, but if you write it out, you might lose information. You don't lose information going in, but on the way out, you might lose some. And later, we will have some examples later where you can play around a bit with these things. And what you can also do once you have like a couple thousand events, you can also like filter these. And we have the syntax. It's the catalog filter method. You only want to select events that are deeper than 100 kilometers with a magnitude of larger than 7. Those should not be too much. And this selects a subset of the previous catalog. Okay? Just dot plot. So all of these methods, they essentially return catalog objects. You can just keep chaining things, and now you have a plot with 2 events, one here and one here. Okay, any questions so far? Good.
What about the Jupyter Notebook? Is there a shortcut for copying and pasting?
Cells or? Oh, in the virtual machine, it's a Control C and Control V. Like you use a Mac, so it's not Command C and V, it's Control C and V.
Oh, okay.
That's just a consequence of the virtual machine. But you can also, wait, if you, like you have this toolbar here, you can copy whole cells here. Now that's copy cell, you can, and then paste it again. But in a normal copy paste, it's, if you're in a Mac and the virtual machine, it's Control C and V. Okay, so now we go. Oh,
Maybe just a question.
sure.
The plot method applies to lots of different objects.
Yes.
Right. So, are there? Maybe we'll get into it later. Different ways to configure plots. Like, say you wanted to change the color coding.
Yes.
Yeah.
There are some ways, like especially the waveform plot that has like 20 parameters. But we are a bit cautious about these. So now we just view, like we don't want to add many more because it gets ridiculous. So now we just view this as a very quick way to view the data. And if people really want a custom plot, they have to do it themselves. We just cannot cover all use cases. But most of these, they have, you can change the protection, the color, the simple things you can do. But for the more complex things, you have to do it yourself. But there's a way to compose event and station plots that works.
They're using MATLAB.
Yeah.
Right?
Yeah.
So you have access to MATLAB.
Yeah.
And can completely customize.
But for the plot, we can just look in the documentation. Stream that plot. You see here, that's the plot method of the stream option. We have all these things here. It's actually super wild. But that's what we learned in the course of doing ObsPy. It's not worth it to cover every use case. Like here, you can configure the tick rotation. It's a bit like the rotation of the label. It's a bit ridiculous. But so if you really need something very specific, you have to do it yourself. But it's easy enough. Okay, so far it has been fairly non-interactive. The next couple of notebooks will contain some exercise, so you actually get to do the things. But let's just serve to give you a quick overview of the core ObsPy classes and how to work with them. You might want to always close and hold the notebook. Make sure they don't running. If you go to this here, you kind of can see which notebooks are running. Like if you have 2 or 3, it doesn't matter. If you have all 10 running, at one point your memory in the virtual machine might be a bit close. Yes?
The CMP catalog was pre-saved. Was it pre-saved?
Yeah, I put it there. But you can get it from the global CMT site. You can download the NDK files there and then you have them. We also have another exercise about how to actually get data. There's a retrieving data notebook. Okay. Yeah, 1 second. Okay, so the next notebook is about dealing with time. So that's in the sense of an absolute time, because you always, as much, you always need to locate the time, the waveforms in time. Otherwise, it's pretty useless. So please click on the O2 UTC datetime notebook. So this one here, handling time. Okay, I realize this is a bit dry, so it's not very exciting, but it's also not very difficult. And it's really crucial that you understand how we deal with time in ObsPy. So the nice thing is that all absolute time values within ObsPy are handled with this class. So anytime you see a time value, be it at the event, the station, or the waveforms, or an algorithm, it's always a UTC datetime object. There's no ambiguity there. It's based on, internally, it's a double precision POSIX timestamp. So it's a Unix timestamp, but we use a double precision floating point number. So we get down to almost nanosecond accuracy. Time zones can only be specified at the initialization time. So the object itself stores the UTC time. It's universal time coordinated, or a couple different names for it. It doesn't have a time zone representation. That's on purpose. If you have data like a certain time in a time zone, you have to specify it at the initialization time. With an ObsPy, it's all UTC. And that's quite nice because you don't need to deal with time zones, daylight saving, all these weird things. You can just ignore them once you have UTC. And that's also consistent how waveform data and station information is stored. So it's quite useful. Okay, once again, just execute this very first cell. Okay, I'm going to quickly show you what the objects can do, and then there are a couple of exercises so you learn how to use these objects. So there are a couple of things when we talk about time object in a sense you want to do. The first thing is you want to initialize or create a time object. So in each ObsPy a UTC datetime object always absolutely represents one point in time. And you from ObsPy you import the UTC datetime object or class, and you initialize in Python. You initialize the class, but just using brackets here and putting in what you want. And all of these four here are exactly the same time, just different ways to specify it. So you can pass a string in a number of formats. So I think that's an ISO some number, I don't know, definition. You can pass a string in that format. ObsPy parses it to its internal floating point representation. Here you see you can pass a time zone. That's exactly the same information, the same UTC time, but in a different time zone. So if you work with time zones, you have to specify it at initialization time. You can also pass a tuple. So it's year, month, day, hour, minute, second, and microseconds. And you can also directly pass the UTC date, like the timestamp itself. If you execute those, you'll note they will all be, well, there's a small error here. I guess it's 200,000. One more. So here these all represent exactly time. There are actually like 5 or 6 more ways of generating time objects. But the idea was just make it as easy as possible to represent UTC time objects, UTC times. Okay, as that should be fairly straightforward. I don't think there are any questions regarding that. Otherwise, please raise your hand. Another thing, the current time in UTC can be initialized by leaving out all the arguments. So you press this, you see here now it's 16:22. We have 9:22, but that's because I think we're behind 9 hours or 8. So this gives you the current time in UTC, not the new local time zone. Okay. Another thing you can do, you can extract information from that. So once you have a time object, here we create it, just say time equals UTC datetime, pass a string to represent the point in time. You can access the year, which is fairly straightforward. In cosmology, you oftentimes tend to need the Julian day, which is the number of the day in the year. So it goes from 1 to 366. You can get the timestamp again, which is the number of seconds since 1960. And there's a couple of other things you can do, like time weekday and whatever. And you can also do, like, again, this is the Jupyter notebook. You can do time dot and then type tab and see all the things you have. There's a couple of other attributes here. Like you have formatting functions for various internal things we need, so we format them for the ArcLink or the old Fisher service and various formatting functions. And you can get lots of other things out of it, okay? And you can also use the string form time and strong p-time methods to customize any way you see fit. Another thing you need to do with times is you need to be able to handle time differences. So difference is either difference between 2 points in time or make a new time object based on time and the difference. Again, let's just create a time object. And you know difference are in seconds. So there's any kind, and you can just add. You can use the time object, add something to it, and what happens, it will give you a new time object X amount of seconds later. So if you need the same time, 1 hour later, you just type plus 3600. The nice thing is this will work across day and year boundaries. You don't really have to worry a lot. It will just work. What it doesn't currently handle are leap seconds. So we're looking into adding that, but it does not handle leap seconds. It has no problem with leap years, but leap seconds are hard, or leap days. It doesn't do leap seconds yet. But that really only matters if you do differences in like 20, 30 points right now. Okay, and again, to get the difference between 2 time objects, now we create a second time object and use time 2, like one object minus the other, and it will give you the difference in seconds between these 2 points in time. Okay, so all that should be fairly straightforward. But you really need to know this to be able to use the rest of ObsPy efficiently. So now there are 3 exercises. I'm going to let you do them. The first one is to calculate the number of days passed since the Tohoku-Oki earthquake. That's the timestamp that was used everywhere throughout this notebook. The second one is you're supposed to make a list of 10 UTC datetime objects starting today at 10, so in half an hour with a spacing of 90 minutes. And the last one is a bit more advanced. It's a list of strings with origin times of earthquakes, and you're supposed to calculate the inter-event time and plot a histogram of that inter-event time. So for all of these exercises, they're by design fairly unspecific. You're supposed to Google how to do things, ask around, because I believe that's really the only way you can learn how to learn it. Okay, have fun.